So I'm going to walk through two papers today in one video, which will be the Statistics and Mechanics papers, May-June 2024 in the UK syllabus 8MA0/2. So let's get on with it. The first question will be statistics, of course. A coach recording the height of some adult rugby players and found the following summary statistics. So we have the median here and the range and the interquartile range. And then the coach also noticed the height of the shortest player is 1.72 meters and 25% of the players are below 1.81. And now it asks you to draw the box and whisker plot, right? So we know the box and whisker plot, we need about 5 things: the minimum, the maximum, the 3 quartiles, Q1, Q2, and Q3. So I'm going to be drawing in my page here, because I guess I can't, well, it's going to take me a bit of time to just copy the diagram and paste it here, so I'm going to be doing here then. Alright, so I'm going to draw the scale quickly. Okay, and I'm not going to probably draw the grid, just marking some points here. So we need a box plot, so I'm guessing it's going to look something like that maybe. Okay, and if we list all the values, so minimum, well, the minimum is already told there, it's 172. Okay, and then the Q1, well, Q1 isn't given explicitly, but it says that 20% of the players are shorter than 181. So we have to know that the first quartile or the lower quartile is 25 percentile. So below the first quartile, that is 25%. So that's telling you that 1.81 is the first quartile, right? So the first quartile is here. So I'm going to mark that as 1.81. Okay. And then the third quartile will be, well, we can find that because we know. Okay, I'm just going to write down Q2 first. So Q2 is just the median. So that's somewhat closer to the Q1. Okay, right there. And to find Q3, right? So we're going to take the interquartile range. So because interquartile range is actually Q3 minus Q1. So we just, solve for Q3. So Q3 is just IQR plus Q1, which is 0.11 plus Q1, which is 1.81. So that's going to give us 1.92. Okay, 1.92 there. So 1.92, we're going to make it as our third quartile. All right, like that. Yeah, so let's draw the middle line here as well. It's just the second quartile. Now the minimum and maximum. Minimum already known is 1.72, so I'm guessing it's going to look something like that. I mean, you can draw in a proper scale, of course, but this is just a diagram, schematic diagram. And then the maximum. So the maximum is, okay, so it's giving you the range. We can find the maximum by just doing range plus minimum, right? Because range is maximum minus minimum, so you should know that. So range is 0.28 plus the minimum. Minimum is 1.72. So that will be 2. So 2 meters is the tallest guy in there. Okay. So I'm just going to maybe have here. And that will be my box and whisker plot. Just done. Okay, so the first question done, guys. Let's go to the second question, question 2. All right. So question 2, Keith is studying the variable daily mean wind direction in degrees from the large data set. Now I know that some people might dish this topic, like they don't even care about this, but I mean, if you try looking at the big picture trend, it's not too bad, right? Okay, for example, let's look at this one. And actually, I have done some research on the large data set and extracted some meaningful patterns. So if you want my notes, just comment large data set, yeah? If there's enough demand, then I'll make it proper PDF and then give it to you guys for free, of course. Okay, Keith summarized the data for Camborne from that year in the 4 directions A, B, C, and D, representing north, south, east, and west. Right. Now you need to know that the wind direction is given as bearing. Right? So you have done that in GCSE, right? Bearing is 0 at the north. So it starts from the north, and let's say if I go to the east, so bearing from north to east will be 90 degrees. So the bearing of east direction will be 90 degrees. So the bearing of south will be 180 degrees from the north. So it's measured from the north clockwise, not anti-clockwise, all right? Okay, so for example, if you take, well, in the table it doesn't tell you the direction, but okay, it tells you the frequency of direction A, B, C, and D. Now, where is Camborne? Camborne is to the very west of the UK, right? I've never been there actually when I was in the UK, but you gotta have some knowledge that in the west, right, somewhat is gonna have some influence from the ocean. I forgot the name of the ocean to the west of that city, but so because it has a large ocean to the west, the wind and the storm and everything will come from there. Now that means, okay, I guess this is kind of like the UK. Sorry about this, about the Brits. Sorry that I draw it quite badly here. But let's say this is the west, right? And you gotta have wind direction from here, and from here. So it seems like the east is probably the least source where the wind comes from. And you can look at the large data set and see the most frequent wind direction. It will be either the south or the west. I don't remember that, but it's either the south or the west, right? In this kind of area. So it's towards the west of the UK. So that means if we look at question A here, using your knowledge of the large data set, state given a reason which direction A represents. It must come from the east, because the east is like, you know, it's just adjacent to the land. It's not the sea, yeah? So Camborne is around here, I guess. This is further west, so Camborne around here. So the east will be, you know, the least frequent direction of the wind. So we are answering question A here, that it will be east because, well, we can say that because it is the wind direction with the smallest, the least, okay, I'm just going to say smallest frequency. And I'm just going to add some information here. Most frequent directions are south or west, right? Because that's the west city, the western city. Okay, and that's done for A. For B, the entry for Hearn on 27th of September 1987 was 999. Okay, so the entry that is talking about here is not the frequency, it's the direction, okay? Because this is just one entry, okay? So it's talking about the actual data here, which is the wind direction. Look, guys, bearing has a maximum of 360 degrees because we measure bearing using just normal unit degree, right? So 999 seems to be an anomaly here. I mean, it's not even an anomaly. It's just a wrong data. Because how can you have a number more than 360, right? So state giving a reason what Keith should do to this value. Well, we say discard, right? So, I mean, ignore seems to be maybe a too strong word, so I'll just say a more proper word, discard. because, yeah, the range of wind direction is 0 to 360 degrees. Yeah, that's just, it's actually a common sense. So if you know a bit about the wind direction, you don't have to memorize anything here. The wind direction is just the bearing degree, the bearing in degree, right? And you already know that from earlier level like GCSE math, right? So I'm guessing that's done for the second question, right? Okay, so we're going to go to the third question now. Okay, so the third question in statistics. Customers in the shop have to queue to pay. To partially complete the table below and partially complete the histogram in the opposite. Oh, it's here, okay. Give information about the time X minutes spent in the queue by each of the 1, 1, 2 customers. 1 day in 1 day, okay. So we have missing data here. No customer spent less than 1 minute, no, or longer than 8 minutes in the queue. So that is just telling you the minimum and the maximum data there. The minimum is 1, the maximum is 8. Okay, and we are asked to complete the table. All right. So the 2 to 3 class here is missing the frequency. So let's have a look at the. Let's have a look at the histogram. I need to hang on. I need to turn do not disturb on first. Okay, let's have a look at the histogram here. Frequency density, minutes. You only have 2 bars here, okay? And seems like we need to estimate. Actually, guys, I'm gonna need to maybe get the diagram into my thing here. Okay, so my diagram here. Here we go. We're going to be using this diagram then. And look at the question here. Okay. So let's have a look. We need to complete the table. So the 2 to 3 class is missing the frequency, so we're going to find it. Okay. There you go. All right, so how do we do this? Okay, so we know the 3 to 4, the adjacent bar there, having the frequency of 13. We are not given the scale, so we need to establish the scale correctly first. Let's count. I mean, I'm guessing that, this is proper. So this is 5, right? And this is another 5. So that's 13. So we know that we should scale it like this, right? And then like this, maybe. So I'm just gonna, and like that, right? So that we can count easily later on. Maybe we can stop there, okay? So the 3 to 4 class has the frequency of 13. That means if we want the frequency of 2 to 3 class, we can just look at the bar here, which tells us that it is 25 on the frequency density. Now you got to be careful. This is the frequency density and not the frequency. Okay, so we need to show some calculation maybe for proper working. Okay, so the frequency of 2 to 3 is going to be equal to the frequency density times the class width. All right, that's just the formula you probably have known already. And that is going to be frequency density being 25, class width being 1. So that is the frequency of the class 2 to 3. Okay, so I'm just going to complete the table, Okay, so question A here, I'm just going to fill in the first blank by just writing the answer right here. And then the other one, we can calculate that. I'm just going to have some more space here. We can calculate that by knowing that the total frequency is 112, right? So the total frequency is 112, but we already know the other classes frequencies. So with the class 2, 3 here, we can find the frequency. I'm just going to find the frequency of the class 4 to 6, which is going to be 1, 1, 2 minus all other classes. So 64 minus the 2 to 3, 25, minus the 3 to 4, 13, and then minus 3. Okay, that's the 6 to 8. So I'm just going to use a calculator here. So 112 minus, what's that? 64, sorry. Minus 25, minus 13, minus 3. That is 7. Okay, so it's 7 here. But, no buts, just we can put 7 down because it's asking for frequency. Now for B, we need to complete this histogram. Okay, there is already a 1 to 2. Okay, so for B, for the frequency density, we need to plot the frequency density for the height. I'm just going to do 1 to 2 here. So the frequency density of 1 to 2 is just the frequency divided by the class width, which is 1. 2 minus 1, right? And that's 64. Okay, so 64 right here is quite high up. I'm just checking if I got it right, like 64 divided by 1, yeah, that's obvious, but there's no tricks here. Okay, so we gotta kind of like aim for higher, so that's 30, 35, 40, 45, 50, 55, 60, 65 right here, so 64 is around here, and it's 1 to 2, so I'm just gonna draw like that, that's one line, and then 64 here, and then the other edge here. Okay, here we go, that's done. Okay, and you guys should use a ruler, right, when you draw this, of course. I'm just checking the scale again. 30, 35, 45, 50, 55, 60. Yeah, okay, that's it. I've drawn the first bar. Now the other missing bars would be 4 to 6 and 6 to 8. Now we got to be careful for 4 to 6 because what we found earlier was the frequency, not the frequency density. So the frequency density of 4 to 6 would be, what was it again? 4 to 6, okay, 7 divided by, well, the class width now is 2, 6 minus 4. Now in this case, the data are continuous, i.e. there's no gaps in between the classes. So that's why the lower bound on this class is 4 and the upper bound is 6. So we can do 6 minus 4 without having to find the lower bound and upper bound. Okay, which is 2 in this case. I'm dividing it by 2, I get 3.5. So 3.5 on the histogram here would be around that, I guess. Yeah, so we're going to draw like that and like that. That's the bar for the 4 to 6. And the 6 to 8, we're going to do the same frequency density. 6 to 8 would be equal to the frequency divided by the class width. 1.5 right here. Okay, and we do the same on the bars. So 1.5 would be around here, and then we draw the width like that. Okay, so that's done for the frequency density, sorry, the histogram plot. Let's do question C. Question C. Ting decides to model the frequency density for these 112 customers by a curve with the equation. Okay, so this one is, giving you the equation where k is a constant. Find the value of k. Okay. Well, guys, for the concept of this one, if you are given any kind of plot, and then it tells you that the y-axis is the frequency density, right? If the y-axis is the frequency density against the x, which is the data, if you integrate an interval, let's say from x1 to x2, okay? If you integrate for the area from x1 to x2, that area will give you the frequency in that interval. Okay, so mathematically we can put that into an expression like this. Okay, dx. So this will be frequency in interval x1 to x2, like that, in a continuous data like this. All right, so that's the concept there. So we can use that frequency density function. Of course, fx is the frequency density function. So if we integrate for the entire domain, which is from 1 to 8, we should get the total frequency of the whole customers. Okay, so we're gonna do integrate 1 to 8, yeah, of that frequency density function, which is k over x squared and dx. All right, putting the bounds in as well, and this should be equal to 1, 1, 2. Make sense? Yeah, because it's the whole frequency there. It's the sum of the frequencies. Okay, so integrating x to the power of minus 2 here. So x to the power of minus 2, so it's the power of, so it's k over x, because the power added 1, it becomes x minus 1 instead. And then we put a minus sign in here because it's dividing also by minus 1. So that is the integral of k over x squared. I put the bounds in 1 to 8 and equate that to 1, 1, 2 because that's given, the total frequency. Okay, so that's just the working there. Well, we can make it look simpler. We don't interfere with the k here. I can pull the k out because we want to find the k and just put 1 here. Okay, so inside the brackets I have minus 1 over 8 minus 1 over 1. Just like that. Okay, so that would become minus 1 over 8 plus 1. So that's 7 over 8. So that means k would be 1, 1, 2 times 8 over 7. Just moving it to the other side to undo the 7 over 8 to find k. So what is that? 7 cancel would be 1, 6. Okay, so that's 16 times 8. I believe that is 128. Yeah, right there. So that would be my answer there. Okay, 128. That's done. So we're gonna move to question 4 here. The random variable x blah blah b, so this is binomial distribution, which is a discrete distribution, 27 and 0.35. So that's telling you the trials, the number of trials is 27 and the probability of success is 0.35. We want to find px equals 10. For question A, I, so px equals 10, so the probability of, hang on, x equals 10 right there. Well, you guys have to know the formula, right? But I just happen to remember the formula, so it's just the binomial coefficient of the number of trials, c, and then the x, which is 10 in this case, and then multiply by the probability of success to the power of x, which is 10, then multiply by the remaining probability, which is 1 minus the probability of success, to the power of the remaining, which we get by 27 minus 10, so that is 17. Yeah, basically that. All right, and I would need a calculator for that. I guess no one can do that kind of math. So we have 27 c 10 here, yeah, and then multiplied by 0.35 to the power of 10, multiplied by 0.65 to the power of 17. So that's 0.153588 blah blah blah. I'm just going to round that to 3 significant figures. Okay, here we go. Alright, so that's I. Well, let's do II. The probability of x in between 12 and 15, not including 15. Well, okay, so let's simplify that problem a little bit. We need to find, I think the calculator can do the work here, but I don't have one that can do this, so I'm just gonna do it my way. in your case, you should use the calculator. So let's simplify it first. So if you have something in between like that, well, you should change it to an equal sign first. So I'm going to change it to less than equal 14 because this is a discrete distribution, right? And that would be equal to p of x less than 14 minus, well, because you are including 12, so you subtract from 11. Yeah, you should subtract from 11. So, and you can do that in the calculator. So just do binomial CD or something, but I don't have the calculator here. This one can't do that. So I have a contingency plan here. Okay, so the way I would do this, so you guys just probably separately find that in the calculator and that subtract each other there, but I'm gonna do it like this. Well, we know that it's a discrete distribution, so that will be equal to the p of x equals 12 plus p of x equals 13 plus p of x equals 14. That's right. I'm gonna just calculate these separately, just in case, right? Because I don't have a calculator that can do that, and that should be accurate. Okay, so it's gonna be just plugging each of them in the formula there. So this is 27, 12, 0. I'm just gonna write p. No. I'm just gonna write 0.35 to the power of 12 times 0.65 to the power of 15 plus 27, 13. Just writing all that, right, guys, for the working, yeah, if you don't mind. And then plus 27, 14. Just running out of space there. Need to move a bit to the left. And then 0.35 to the power of 14 times 0.65 to the power of 13. That's right, I'm going to calculate all of them. Because my calculator can handle that, I hope. So just going to do 27c 12 times 0.35 to the power of 12 times 0.65 to the power of 15 plus, right, that's the first term, 27c 13 times, move to the left here, where are we now, 0.35 to the power of 13, move it down, times 0.65 to the power of 14, move it down, plus 27c 14. We gotta really be careful about pressing the calculator here, guys, because I'm sure you have made a mistake in the calculator error before. I mean, pressing the wrong thing, not checking what you did press, you know. We have that happens. So we gotta be careful. 0.65 to the power of 13. Okay, I'm just double checking. I think I'm happy with all that. Let me just move the cursor to check the earlier term. 14, 13. Yep. 13, 12. Yep. So we get, what was it again? 0.179472 blah blah blah. Gonna round that to 0.179. Three significant figures. Okay, so that's number 2 done right there in part A. Historical records show that the proportion of defective items produced by the machine is 0.12. Following the maintenance service, the maintenance random sample 60 items is taken and 3 defective items are found. Okay, we're gonna move to the next page now. Carry out suitable tests to determine whether the proportion of defective items produced by the machine has decreased following the maintenance service. Okay, so hypothesis testing here. Now we should write the, I'm just going to do y here because x is already used. We should write the statistical distribution first. So this is binomial again, right? So we're going to use B, and we have 60 items, so I'm going to do 60 there, and the probability of success is 0.12. Hypothesis H0 is, well, we are assuming that it is still 0.12, right? The probability of defective items. So we just do P equals 0.12. Yeah? Okay. And then the alternative hypothesis is P what? The defective items produced by the machine has decreased. Okay, that is the thing we want to test, whether the proportion decreased. So this should be less than 0.12. So at first the proportion is kind of like 12%. Now with 3 defective items out of 60, we're going to see whether that is significant enough to reject the null. All right, so we calculate the probability. Yeah, again, we're going to use binomial, and I don't have a calculator again to do that. So we're going to calculate the probability of x, because this is a left tail, right? It's a less than. So we do x less than or equal 3, because that is the number of defective items in the sample, right? And we find that. Again, because I don't have a calculator to do that, so I'm just going to, list all the possible P's there. Just like that. Just 4 of them, that's fine. I mean, I can handle that. So we're going to do the same. After we find the probability of x less than or equal 3, we're going to compare that to the level of significance given there as 5%. And then we're going to determine whether there is enough evidence to blah, 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 right? That's the pattern there. Okay, so this will be equal to, so 60, 0. 0.12 to the 0 times 88, right, to the 60. 61, 0.12 to the 1, 6.88 to the 59. 62, 0.12 to the 2, 0.88 to the 58, and the last one, 63, 0.12 to the 3 times 0.88 to the 57. Now, if you have learned the way the binomial coefficient works before, when you have NC0, it's going to give you 1. NC1 is going to give you N. So I know that this term here is going to give me 1 without doing the calculator there. And this is 1 anyway, so this will just be that, right? So the first term I just put in the calculator, 0.88 to the power of 60. I mean, you can put the whole thing in if you need security, but because we have some knowledge that, I have some knowledge that is 1 and 1, so I don't need to. I can save some time by not pressing too many things there. So that's the first term there. The second term, again, as I told you, the 60 C1, yeah, the binomial coefficient for the second term there is going to be 60. You can try that if you don't believe me, and you shouldn't believe me, okay? 60 times 0.12 to the power of 1, so I just leave it there, and 0.88 to the power of 59, yeah, plus 50 C2, yeah, times 0.12 to the power of 2 times 0.88 to the power of 58 plus, what's the last one? 60 C3 times 0.12 to the power of 3 times 0.88 to the power of 57. That's it. So that is the probability there, which is 0.060131, blah, blah, blah. I'm just going to round that to 0.0601. Again, 3 significant figures. Calculator is done. Okay, there you go. Now, of course, we know that this is larger than the level of significance, right? So 0.0601 greater than 0.005. So we reject, no, not reject, we accept, right? Because it's not smaller. We only reject when it's smaller than the level of significance. So we accept H naught. And then we say there is not enough evidence to suggest that there is a decrease in the proportion of defective items, to suggest that the proportion of defective items decreased. Okay, that's it. And that's part B done. And part C, I'm going to put it here. Write down the p-value for your test in part B. Well, basically this is asking for the probability that would have made this critical, right? So for example, if we were able to choose the significance level by ourselves, what is probably like the maximum, right? What is kind of like the maximum level of significance? I mean, in reality, when this hypothesis testing concept is used in real life, the higher the level of significance, the worse, in terms of the level of confidence that you can be so sure that in this case, that there is a decrease. So if you change this question to 2.5%, and let's say it was significant that you have to reject the null, you can be more confident that it is actually decreased, the proportion of defective items. If you, however, changed it to 10%, then that would be, you would be less confident, although it was significant. So when we choose the significant level ourselves, we should be conservative, as in we should choose not a too high level of significance, right? So here, the value that would have made this sample, like the 3 defective items out of 60, that would have made this sampling significant, so that we could suggest that that would have been significant so that we reject the null, would be just about the same value that we calculate the probability here. So I'm just saying it's just 0.06. So it's basically 6% rather than 5%. So if we chose 6% for the level of significance, then the whole sampling there would have been significant, and we would have rejected the null hypothesis and hence suggested that there is a decrease, right? So basically that's the answer. All right. And number 5. I guess that's the last one in statistics, and then we can move on to mechanics later. All right, so what have we here? We have a probability question. A biased four-sided spinner has the numbers 6, 7, 8, and 10 on it. The discrete random variable x represents the score when the spinner is spun once and has the following probability distribution. Where q is a probability, it's an unknown for the time being. A, find the value of q, so hence we need to solve it. Okay, well, you look at the table there. There are 2 q's there. And you need to know that if you add up all the probabilities in any sampling distribution, this is called probability distribution or sampling distribution, you should get 1. So we're adding up 0.5 plus 0.2 plus 2 q's to be 1. Okay, so 2q is equal to, subtracting 1 by all that, we get 0.3, so q would be equals to 0.15, sorry, 15. Yeah. Okay, I'm happy with that. That's just A, yeah? B. Karen spins the spinner repeatedly until she either gets a 7 or she has taken 4 spins. B. Show that the probability that Karen stops after taking her third spin is 0.128. Okay, so this is like keeping spinning. Once getting a 7 will stop, right? So after she gets a 7, when she gets a 7, she will stop. That means if she gets a 7 on the third spin, the first 2 spins will not be a 7. All right? So the probability of being 7, yeah, is 0.2. That means the probability of not being a 7 could be anything else, 6, 8, and 10, is then 1 minus that, so which is 0.8. So the probability of stop after the third spin, so P stop at third is equal to, well, the first 2 is 0.8 and 0.8, right? Okay, and then the third spin is then a 7, which is 0.2. And I believe that should be, yeah, 0.8 to the power of 2 times 0.2. There you go, 0.128 as required. Question C. Okay. The random variable S represents the number of spins Karen takes. Find the probability distribution for S. Okay. So, yeah, this is going to be different from the table you're given there because we're dealing with the number of spins that actually occurs. Okay, so if I do a table like this, we're going to have a little s here. And on the second row here, we have big S equals little s. So a little s can be what? It's just the possible outcomes, right? So can we start from 0? That means 0 spins? Not possible. She has to spin something. Okay? So the smallest number of spin would be 1. And then 2. So 2 means that you will get a 7 on the second spin. And 3, we already did 3 there. And 4, probably not to scale table here. So for S being 1, that means she gets a 7 on the first spin. How lucky. And the probability of getting a 7 on the first spin is just, 0.2 there. We don't need to calculate anything because, it's just 0.2 and then that's it because you stop there. On the second spin, however, if we do P S equals 2, you're going to have to get a non-7 on the first spin, which is 0.8, and multiply by a 7 probability of 7 on the second spin. And that's it. So that is 0.16. Okay, so 0.16 here. On the third spin, we already did that, is 0.128. And the number of spins here being 4, not to mean that she gets a 7 on the fourth spin, but she could also not get a 7 on the fourth spin. So there is no 5 or 6 or 7 for the value of S because she stops. So on the fourth spin, whatever she gets, she stops spinning. We can calculate that by just subtracting everything else from 1, yeah? So that includes get and not get a 7, yeah? We're just going to use a calculator for that. So 1 minus, 0.2 minus, 0.16 minus, 0.128. That is 0.512. Okay, we put it here. That's it. Okay, so I'm done with the probability distribution because that's what it is, the table. Okay, D. The random variable N represents the number of times Karen gets a 7. Okay, so yeah, I mean, if you think about it, let's do a table. So a little n, p big N equals a little n. How many times can she get a 7? Of course, she can get no 7 if for 4 spins she get non-7 for all of them. And that's a bit unlucky, right, if you think about it. Or she can get 1 7 and stop, because she can't get 2, can she? She can only get 1, because once she gets 1 7, she has to stop. So the only possible outcomes for n would be just 0 and 1. That's it, right? So what would be the probability of getting no 0 at all? Well, that is when she has to spin 4 times and get no 7. We haven't had that, so it's p n equals 0. No 7 at all, so we do 0.8 to the power of 4, right? So 0.8 to the power of 4 is 0.4096. That's it. So that means the remaining, which is p n equals 1, would just be 1 minus that. Okay, which is, if we do that, minus 1 right there, that would just be that. Okay, there you go. So we can just put it in the table here. I mean, for later use, I think. There you go. I mean, it doesn't ask you to tabulate or make a table for probability distribution there, but I just, making it for you so that you see what happens here. Now, what we want is actually to find the probability of S greater than N. Now, as you can see, to have S greater than N, you gotta be careful. S is the number of spins, while N is the number of spins she gets a 7. Sorry. So, what are the possible outcomes for S and N so that S can be greater than N? So, if she spins once, at maximum she can only get 1 7, right? So, I mean, you can't really have the cases where N is actually greater than S. N is the number of times she gets a 7. S is the number of times she spins. So if she spins 4 times, she can't really get 4 7, right? So N is usually less than S, because once you get 1 N, which is N being 1, she has to stop. That's why N, maximum N here is 1. Now let's think about, for each case of N, what can S be? So if N is 1, okay, if N is 1, S can be what? Oh, let me do a tree diagram like this. So this is N, this is S. So if N is 1, S can be, 1 or 2 or 3 or 4, right? If N is 0, S can only be one thing, 4. Because if she doesn't get a 7 yet, she needs to keep going. So N is 0 can only happen when she, uses up the quota of spinning, which is 4 times. Okay? So what is the case where S greater than N? Well, we have a lot. So S greater than N is just 2 and 1, 3 and 1, 4 and 1, 4 and 0. So that's almost all of the possible outcomes between N and S, right? But there is only this, which is not possible. So we're just going to do 1 minus this probability right here, where the number of spin is the same as the number of 7s, which is 1 and 1, right? How do we get 1 and 1? Well, that would be when she spins a 7 on the first spin. She gets a 7 on the first spin, which is what? 7 on the first spin is 0.2. It's this guy here. That is very lucky, right? So we're just going to do 1 minus that, because that is the only case where S is not greater than N. And that's just a smart way to calculate this. I mean, that's why it's 1 mark. 1 mark doesn't necessarily mean it's easy, but just the amount of work you need to show is small, but not necessarily the amount of thinking. So you got to be careful here, right? It doesn't mean it's easy. It's just that you probably don't have to write a lot, right? So that's 0.7 is the answer. Okay, I'm done with that. Okay, so that's all statistics, guys. I'm just going to change it to change my thing first. Mechanics. Here we go. Okay. All right. So this is a mechanics paper. I'm just going to do in the same sit here. This is on the same year, same round, right? But I guess you have to do 2 papers all at one sit. Okay. Mechanics. First question. We have a motion graph. Figure 1 shows the speed-time graph for the journey for a car moving in a long queue of traffic on the straight horizontal road. At time t equals 0, the car is at rest. Okay, hence shown by the graph. I mean, the graph already speaks volume about the information here, so we probably don't need to read all of that. So we find the distance AB. All right, so question 1A, find the distance AB. Just going to label this mechanics. All right. Okay. So find the distance AB, right? Okay, so the area under the speed time graph is the distance traveled. Because this is in one direction, so we can assume the distance AB will be, basically the area. I mean, in a higher level mechanics, sometimes you don't move in a straight line. All right? Okay, so distance AB, area, so it's the area of the trapezium there. I'm just going to do 1/2 times the height of the trapezium is 5 times the sum of the parallel sides. So the top side here, the top of the trapezium is 20 minus 5, so that's 15 plus. The bottom is from 0 to 30. Okay, so that's the area, the distance AB equals that. Calculator. So it's 1/2 times 5 times, what was it again? 15 plus 30, 45. Okay, so that's 112.5 meters. B. Sketch the distance time graph for the journey of the car from A to B. Okay, so this one might be a little tricky because you have changing in speed. You have change in speed. So that means when you draw the distance time graph, it's not going to be a straight line. It's going to be a curve. Okay, it's going to be a curve. Just excuse me for 1 sec. Okay, I'm back. So it's going to be a curve on the part where the speed is not constant, like from 0 to 5 to 30 here. That's time in second, and that will be distance in meters. Okay, from 0 to 5, we need to calculate the distance traveled. So we can do d from 0 to 5 being the area of that triangle there, 1/2 times 5 times 5. That is 12.5, right? It's just 25 over 2. So we're just going to draw the curve first. Now, you need to know that when you find the area of a triangle, that is just like integrating. Yeah, so if you look at the motion graph there, the speed time graph, you are finding the area of this, right? I mean, technically, mathematically, you can also do that by integrating the linear function here on the first bit. Integrating linear function of a positive gradient here, let's say, for example, if it's, say, 2x, if you are integrating 2x, you're going to get a parabolic function, you're going to get x squared, right? And that is like this. It's like a concave curve, if I'm not mistaken to say that. Yeah, basically it's a normal parabola shape. So it's going to look like that with a curve like that. Just going to make it like that. Yeah, and this will be the distance traveled there, which is 12.5. All right, there. And then it's going to continue because the speed is continuous there. So it's 5 from the first part. And then you got to continue the gradient here. So the gradient, when you continue with a straight line, so when you integrate the constant speed part there, you get a straight line. You get a linear, right? So now distance will increase with a constant rate because there is a constant speed. So just drawing like that up. Yeah, I should make the gradient the same. Hang on. Maybe I should move this down a bit. It's going to be a little tricky if you want to make it so perfect, right? So that's a curve. And then I'm going to make the same gradient here up. Yeah, supposed to be the same gradient there. I'm just going to make it look the same. Yeah, there you go. And this will be up until the 20th second. Okay, what is the area? So d from 5 to 20 is the area of that rectangle, which is 15 times 5, which is 75. Sorry, 75. So that means if we add 75 to 12.5, we get 87.5. Yeah. So 87.5 right here. Yeah. Okay, 87.5. Is it? Yeah, 87.5. I'm just checking. Yeah. Okay, and then you gotta do, well, I think the last part is easy because we know that the distance traveled should be 112.5. That's the whole thing. So again, but now this time speed is decreasing. So it's like if we want to find the area of that last part, decelerating part, it's like we are integrating a negative linear equation like that. So you're going to get a negative quadratic, which means it should be a convex like that. Yeah? Just the opposite way to curve, right? So I'm just going to do that and maybe change this bit to like that. Yeah, just to get an idea of the curve there. I mean, we don't have to make it so perfect. Just like that, okay? Just make it look like a curve. And of course, that should be our 112.5 distance traveled. Okay, and that's done. That's the entire curve. Done for B. And done for number 1. Let's go to number 2. Number 2. A particle is moving along a straight line at time t seconds, t greater than 0. The velocity of the particle is v meters per second, where v is that function right there. A, find the acceleration of the particle when t equals 4. Okay. So you have to know that to get the acceleration in kinematics, given a velocity function, we need to differentiate the velocity function. So A equals dv by dt, where v is the velocity function. Okay, so integrating 2t we get 2, right? Sorry, differentiating 2t we get 2. Differentiating the root t there, root t is just basically t to the power of a half. So we differentiate t power of a half, we bring the power down, so it's 7 over 2 as we bring it down. And power subtracted by 1, so it's minus a half instead. 6 goes away. So that is the acceleration function. And then we solve it when a of t equals 4. So I'm just going to write a4 like this. Okay, would be equal to 2 minus 7 over 2. T equals 4. So t to the power of minus is basically 1 over t to the power of half. A power of half means a square root. So it's a square root of 4 when t equals 4. So that is basically 2 minus 7 over 4. So that is basically 1 over 4, which is 0.25 meters per second squared. Okay, I'm done for A. For B, given that the particle does not come to instantaneous rest in the interval 1 to 2. Okay, so that is telling you that, okay, we want to show that xy is that meters. So this is basically asking you to find the displacement from x to y, right? It's telling you that there is no instantaneous rest because it's probably helping you so that you don't need to think about the turning point. So for example, if there was the instantaneous rest points between 1 to 2, the graph might look like something like that. So you would have a little work here to work out that area there and that area there. Because for example, if we want the distance traveled, right? Let's say we want the distance traveled rather than displacement, then you would have to add them up. Or if you want the displacement, then these two areas will cancel out. They will they will have to subtract each other, yeah, rather than adding up. So we're not having that, right, in this one. So we are fine. So we are just integrating, yeah. So xy would just be to integrate from 1 to 2 of the velocity function, yeah. Just gonna change it to an index form here. Oh, I forgot the 6. And then we don't need to find the c constant because this is definite integration. So just that, and that's fine, yeah. Okay, so distance xy, yeah. All right, so integrating first, we get t to the 2 here for the first term. So it's 2t to the power of 2 divided by 2, 2 cancels. And then that is t to the power of half, so adding 1, we get 3 over 2. If we divide by 3 over 2, we're going to get 2 over 3 multiplied 7, that is 14 over 3, yeah? T to the power of 3 over 2 instead. 6 becomes 6t, okay, after integration. And then I'm going to sub 1 and 2 in there. All right. Substituting the bounds. Now, the way I do the bounds here might be a little different to other people. So I prefer doing term by term, not by bounds. So people would normally do sub in the upper bound first, yeah, for all the terms, and then subtract by subbing in all the terms by the lower bound. But I do like this. So for each term, I do 2 squared for the t squared here and minus already. So it's the same, but you just sort of like tidy up the lower bound terms and move it to the similar term, subtracting the upper bound already. So I'm done for the t squared term. So that's the t squared term. And then minus, I'm just going to move 14 over 3 out here. And then the t to the power of 3 over 2, I do 2 to the power of 3 over 2 minus 1 to the power of 3 over 2. So that's done for the second term. And then for the third term, 6, 2 minus 1. So you see, I subtract each term, right, just term by term, using the bounds on each term, not going for all terms and separated by the upper and lower bounds. Okay, so there you go there. So what is this? 4 minus 1 is 3, right? Yeah. And then that is, so we need to get the exact form, so using a calculator won't help much. 2 to the power of 3 over 2, so that's square root 2 to the power of 3, so that's 2 root 2. So 2 root 2, I'm just going to maybe expand that. So that multiplied 2 root 2, and minus times minus is a plus. 1 to the power of anything is 1. So I'm just going to leave it at that. And this is 6 times 2 minus 1 is 1, so that's just plus 6. All right, so grabbing all the numbers together, we get 3 plus 6, which is 9, and plus 14 over 5. That is going to be 27 plus 14 is 41. Yeah, I'm getting 41 here. 41 over 3 minus 28 over 3 root 2. If we factor 1 over 3 out, we get exactly the same. Yep. Okay, so we get as required. That's number 2 there. Number 3. Okay, in this question, I and j are perpendicular unit vectors in the horizontal plane. A particular particle P is moving on a smooth horizontal surface under the action of 2 forces. Given that the mass of P is 2 kilograms, the 2 forces are that and that, where C is a constant. The magnitude of acceleration is root 5 meters per second squared. Find the two possible values of C. Right, so this is Newton's second law straight. Sigma F equals ma. For those of you who do physics and mechanics, you should know that. Sigma F is just the sum of all the force vectors, right? So I'm just going to do in a column form here. So this is 2 and 4, I and j, vertical, like that, plus C and minus 2, yeah, adding them up, where C is unknown. And mass is 2. Well, acceleration is, for the time being, unknown. So I'm just going to do AX and AY there. All right. We can already find AY right here. Because when we write it like this, we can do a vector method where we separate the two axes. So that means if you do 4 plus minus 2 for the y direction, for the j direction, yeah, for the j direction here, that's going to be equals to 2ay. Well, 2 here we'll still have to multiply across all the ax and ay. Well, that gives us ay, right? So ay, which is the acceleration along the j direction, would be 2 divided by 2, which is 1. We get one of them. Now, that is when we're going to use the acceleration there, right? The ax and ay. Because we know that the magnitude, a, is from doing the Pythagoras between ax and ay. Yeah? Yeah, because ax and ay are just 2 components of the acceleration. If we do Pythagoras, we should get the magnitude, which is equal to root 5 as given. So that means ax squared, which is still unknown, plus ay, which is 1 squared, equals 5 squared. Sorry, root 5 squared being 5. Well, that means ax squared is just 4 if you just subtract 1 from 5. Well, that means ax is just plus or minus 2, isn't it? Right? Ax is just plus or minus 2. Don't forget, when you square root both sides, you get 2 values, mostly. But sometimes you do get 1 because there is an exception to the question. But this case, there is no exception there. So acceleration can be plus or minus 2 in this case. Now, but we don't want, it doesn't ask you for ax. It asks you for c. We got to use ax here to find the c. So we plug it back to the very first equation we set there. So if you only look at the x component, 2 plus c equals 2ax again. So c would have to be equal to 2ax minus 2. So if we plug 2 values of ax in, we get 2 values of c. So c would be, let's plug 2 in first. Plugging 2 in, we get 2 times 2 is 4, 4 minus 2 is 2. Plug the second value in, minus 2. 2 minus 2 is minus 4, minus 2 is minus 6. So it's 2 or minus 6. That's it. Okay, so that's done for number 3. Number 4. Okay, here we go. Figure 2 shows a car towing a trailer along a straight horizontal road. The mass of the car is 800, blah, blah, blah. Towbar modeled as a light rod. the resistance to the motion of the car modeled as a constant force, blah, blah, blah. Okay. So guys, you can just take your time to read the question here. I think I'm done. So for A, we need to find R first. Well, we have a car here, so I'm just going to draw a car bigger because the mass is greater than the trailer there. The trailer is a little guy. Okay. So there is an engine force driving the car forward of 1740 newtons. And then there is a resistive force pulling the car backwards of 400 newtons, right? Where there is also a resistive force pulling the trailer backwards, which we want to find in question A first. Okay. And the acceleration of the motion of the system, this is a connected particle system, right? Is given to be 0.6 meters per second squared. So since it's asking for x, we can do system first. Because if it's asked for t, then we should do separate. But this is asking for s. So we can ignore the t by now. The t, for now we can ignore the t. The t is the tension between the tension in the towbar, basically. Okay? So we do sigma f system equals m system times a system, basically. So sigma f system, you just consider all the forces that act on either object, yeah, which is 1740 here pulling to the right, but then we have to subtract 400 here because it's working against the driving force, and also the r. That's probably it for the forces. M of the system is the sum of the masses, being 800 plus 600, right? And then the acceleration is already given to be 0.6. So that, right? So R is equal to, doing the math there, it's just 1740 minus 400, minus, that's 1400 times 0.6. Okay? So 1740 minus 400 minus 1400 times 0.6. 500 there. And so required, right? Part B. Find the value of T. Now tension. So we can pick either one because we already know R as well. So I'm just going to do trailer, yeah? The little guy. 500 pulling back and the tension pulling forward. Nothing else. Acceleration still the same, 0.6 meter per second squared. So sigma F trailer equals M trailer times A. Sigma F is T minus 500 equals M of the trailer being 600 times the A, which is still the same because this is a connected particle system. So tension would be 600 times 0.6 is 360 plus 500. That is 860 newtons. Okay. Yeah? So that's tension there. Done for the first two parts. And now on to parts C, D, and E. Okay, so let's do part C here. Show that after the towbar brakes, the deceleration of the trailer is 5/6. So at the instant when the speed of the car and the trailer is 12.5 meters per second, the towbar brakes, the trailer moves a further distance d before coming to rest. The resistance to the motion of the trailer is modeled as a constant force of magnitude 500. Well, that is saying that the resistance to the motion of the trailer is still the same. Okay, so if you still have that resistive force on the trailer being 500, right? But the motion is still going at 12.5 meters per second there. You don't have any other forces acting on its own engine. So it can't have any forward driving force. That means the sigma F here will only be, again, sigma F equals MA. The sigma F here can only be minus 500 because it's working against the motion. So that's decelerating force. Equals m is the same again, 600 times a. So a here, just do the number there, we get negative 5/6 meter per second squared. And that is implying that it is decelerating, of course. Okay, so that's it for C. D, find the value of D. So D is the distance moved before coming to rest, right? So this is SUVAT, okay? This is SUVAT, because you are given the velocity there. You know that if we draw everything out here, S we want to find, U is 12.5. That is just when the towbar breaks. V is 0 because you need to stop somewhere. A is negative 5/6, right? And T, we don't care, we don't want, nothing to do with it. So which equation in the SUVAT equations has these four or doesn't have T? Well, that's only one. That one, right? That's the way to go. So substituting V0, U 12.5 squared there, plus 2, A is negative, and S is what we want. Just going to have to be careful between, I'm just going to have to be careful between S and 5 here. Okay, so S will be moving on the other side, 12.5 squared divided by 2 times 5/6. Everything will be positive there. Okay, so I'm just going to use a calculator there. Fraction 12.5 to the power of 2 divided by 2 times 5/6 down here. So that is 93.75 meters. That is the value of D, yeah? Distance traveled before stop. Okay, and then the last question here, I guess, guys. In reality, the distance D meters is likely to be different from the answer found in part D. Okay, give 2 different reasons why this is the case. All right, guys, that's quite a number of ways you can answer this, but I guess if it asks for 2, you need to give 2 unique ones. Don't give more, because sometimes if you give more, you can get penalized, right? So I think, well, it's not like, okay, usually people would go with air resistance, but in this case we can't really say that the question ignores air resistance, right? It doesn't say anywhere. Okay, plus there is already a resistance to motion of the car, so air resistance might be included in there, that term. Resistance to the car and the trailer. Okay, but there's a problem, because look, no matter what speed they're moving at, those resistive forces are the same. Yeah, for example, we keep R here the same value when we do the part C and D, right? If there is a resistance included in that term, that means it shouldn't be constant, because don't forget, air resistance changes with the speed. Imagine you moving, you're running. If you run slow, you're not going to feel so much air flowing, hitting you. But if you run faster, you can feel that now your hair is going to, get blown a bit by the air and everything, the wind. So when you move faster, air resistance should be greater. Vice versa, when you move slower, air resistance should be smaller. So I'm just saying that the resistive force here, so first, the resistive force, yeah, on trailer should not be constant. That's it. That's the first reason. It doesn't have to talk about air resistance, but we know that if air resistance is included in there, then it shouldn't be a constant. Let's talk about the second one. Okay, let's see. Well, don't forget, because I spotted at first that we model a towbar as a rod. a light rod. Yeah, light means we are ignoring the weight of the rod. You see, although the towbar breaks, but when it breaks somewhere in the middle. It might be off from the middle, but you know, that's the idea. It's not going to break like towards the end of the left edge here. Maybe not. That's unrealistic. So when it breaks somewhere in the middle, that means the trailer will carry some weight of that towbar along the way. So the mass might not be 600 now, maybe 600 and a bit more. So that makes it unrealistic here. Yeah. So the towbar has a mass, hence weight. So weight, so the overall mass of trailer is more. I'm just going to write simple like that. So basically it's more than 600. Okay, that's why it made it a little unrealistic there. That's why it would make D different from reality there, the one we calculated. So it might be smaller in that case. Okay, so I think I'm done. And yeah, so I hope that was useful for all you guys. And thank you for watching up to this point. And there's more to come. If you have any question on this walkthrough or anything that I, showed the working, you can give me a comment and I'll make sure I'll reply all the comments by myself. And I'll see you in the next video.